It's good to be back. It was a good trip, but it was it was like a nationwide conference on schools that installed solar and batteries and renewable energies and electric school buses. And so it went well. It's like, we got the 2 big arrays, which is more than about any other school has in the entire Midwest. And what made it unique is that all the other schools that had them, like they paid for them, like the district just wrote the check. And I said, well, how'd you finance yours? I said, well, I've done a lot of stupid things. I've gotten tattoos. I've dyed my hair, collected money.
You got a tattoo?
Yeah.
Really? No.
Yes.
Oh, wow.
There's the tattoo. That's a whole other long story
Nice.
about how that came to be. That raised $3,000.
I bet you should get another one.
Huh?
I said you should get another one.
No. One and done. That was it. Nope.
Teardrop?
Yeah. Well, no. It was what was suggested is that now that we have 2 different solar arrays going, this one and the one I play Woodman, is that instead of a teardrop, I get like a solar panel.
Oh.
For every time we install a solar.
Yeah, your whole face.
Yeah, every time we get a solar array, I get a solar panel instead of a teardrop. So that would just get really fast. But on that tattoo, there was probably a half a dozen people that heard about it, came up and said, "Can we take a picture of your tattoo?" I was like, okay, kind of creepy, but okay, if that's really what you want to do. So anyway, so it went well, and we'll talk about the solar project once I have time to catch my breath, and we'll go over all that. Okay, so everything, y'all hate being gone, passion. There's so much work to be gone. So how far did y'all get through the videos? Y'all okay with where we're at? Okay, so let's do a quick summary of what I hope you all realize. Is that, first off, when you look at like the difficulty of what was happening, so if you haven't seen this on the news or Twitter or something, there's 5 planets in the evening that are all aligned, pretty much aligned. They're all 5 visible at the same time. And so if you look at it, and they're visible like in the western sky, okay, like Venus, for example. So what that means is that here's the sun, and here's the earth, and these views are always looking down from on top. And the earth spins counterclockwise, which is why the sun rises in the east and sets in the west. That's how we know it spins in that direction. So the earth is coming around like this, and so if you're over here, that means that's midnight, because you're on the direct opposite side of the sun. If you're standing here, that's straight up noon, boom, that's where that's located. So you come around here, like in a counterclockwise direction. So if you're here, this is where you're going to see the sun setting. So in the night sky, all of these planets are visible above the western horizon. So what that means is that all of these planets are somewhere out here in their orbit, okay? Now, except for, no, I'm sorry, because Venus is here. It's visible just after sunset. I was thinking sunrise. So what that means is all of these planets are somewhere out there. And so when you look at what Kepler was able to do, it wasn't cool that, okay, you see Venus, but try and triangulate that. It's like, okay, well, that's cool, but how do you know the orbit of Venus? How do you know the edge of that orbit? Because you can observe it, but if you've ever looked at like planets or anything through a telescope, it's cool, you can look at them, but just to see them, because the distances are so great, to try and realize, wow, this is how far apart they are. That was the hardest part, was that, okay, he stole Tycho Brahe's data, which was a great story of intrigue and espionage, and then he spent years and years and years doing these calculations. But that was the hardest part, is like, how do you determine the edge of that orbit? Because it isn't like you look at it and go, oh, here's a line, and this is a track that is going in. Okay, so like if I see, Carson running around this room, I know that, oh, she's got to be at the edge of the room, okay, because I can see the edge of the room. But if I just see Carson running, I don't know, it's tough for me to get a feel how far away is she. And so not only are you dealing with that, but Kepler's famous statement was that he waged war on Mars. because Mars was the closest planet that was outside of our orbit. So the only time you really couldn't get any observational data on Mars is when it's directly behind the sun. Even if at any other point in that orbit, you'll be able to at least see it for a while. Okay, maybe not very long, but at least you'll be able to see it. Venus and Mercury are tough because the sun's in the way, okay? And so the Earth was tilted on its axis. The Earth is spinning. The Earth is traveling in its own elliptical orbit, okay, which means that it's speeding up and slowing down. Mars's eccentricity is about 10%, which is a good thing because they figured if the eccentricity had only been about 5%, he wouldn't have had a good enough data to realize it was an elliptical orbit. He probably would have thought it was a circular orbit. But because Mars's orbit was so elliptical, he was able to pick that up even with the relatively, advanced but yet crude data from Tycho Brahe. So the first law says, hey, they travel in ellipses. That kind of made people mad because, hey, the heavens were the realm of the gods. The circle is the perfect shape. They're all equidistant apart. It has no beginning. It has no end, whatever, okay? So in an ellipse kind of implies that, hey, God was trying for an ellipse or trying for a circle, kind of had an off day, had to settle for an ellipse. That created some controversy. The hardest part, and this was the calculations that you all did, said, okay, the planets are speeding up or slowing down. Now, if you look at what Kepler did, Kepler kind of said, I'm not going to try to explain why this works, okay? This is before Newton, there was no knowledge of gravity, there was no law of conservation of angular momentum, conservation of energy, nothing like that. So Kepler pretty much said, here's the deal. This is what it's doing. I really don't know why it's doing it, but this is what it's doing. Okay, and later on we figured out why those planets were doing what they were doing. So here's all I want you to remember, is that when any planet is farther from the sun, that's when it is moving slowest. Okay, so the farther it goes, the slower it goes. And then the closer it gets, as you decrease that radius, you increase the velocity. So here's kind of an analogy that I can make. If any of you have a set of stairs in your house, and you might have like a corner banister, and you might have done this as a kid, especially it's fun to do if you're in socks. And you run up and you grab a hold of the banister and you slingshot yourself around, and you grab the edge, okay, you swing yourself around. That's kind of what the analogous to what the planets do. Okay, the planets use gravity to slingshot themselves around. So they grab a hold of the sun, boom, they slingshot themselves around. The other idea we'll get into later is that it's conservation of energy. Kinetic energy is the energy of motion. So when the planets are closest, that's when they have their highest amount of kinetic energy, because that's when they're going fastest. When they go further away, it's like pulling a rubber band and you're stretching it. So then you're storing potential energy as that rubber band gets stretched. But the sum of those two values always add up to equal the same. So you're always exchanging one for the other. You're always exchanging kinetic energy for gravitational potential energy. So mathematically, that law of equal areas and equal times, so it doesn't make any difference what that is. When the lab, Mercury has a relatively short orbit, okay, 84 days is one it's about 88 days. So that's closest to the sun. So when you do that calculation of Kepler's law on that second page, when you do like period of Mercury squared over period of Earth squared equals radius of Earth cubed over the radius of Mercury cubed, that period of Mercury should have worked out to have been 88 days, okay? And which should match the observational data. So this is the only one that's mathematical in terms of a ratio, like I said. And you'll see in contrast the different situations. But with this one, this is the only time I will ever tell you this in this class. It doesn't make any difference what the units of period are in, as long as they're the same. Days and days, years and years, hours and hours. Okay, it doesn't make any difference, okay, because it's a ratio. The same thing is true of distances, okay? Kepler used astronomical units because he didn't know the number. He couldn't ask his phone and go, hey, Alexa, what's the distance between Mercury and the sun? Okay, didn't know the numbers. So he goes, well, it's a ratio anyway. So he just set the distance from the Earth to the sun to be 1 astronomical unit. And then he said, okay, well, everything else then has to be less than that. So Mercury and Venus obviously have astronomical units less than 1. Mercury, Jupiter, Saturn, all of those then have multiples that are bigger than that. Because it's a ratio, it didn't matter because it's a ratio. Okay, so that's the only one that's mathematical in nature. Okay, so should see that you get about 88 days. Boom, here we go. Now we're historically. So here's where we're at. Tycho Brahe has passed away. Kepler stole the data, went back to Germany, crunched the numbers, published his works. There says this is cool. So this was in like the early 1600s. Okay. And that was a tough time to be alive. There was like the plague and civil war, and they didn't have calculators or Oreos, and survival was tough. So then Isaac Newton comes along, and he has this law of universal gravity. So in terms of all the equations I'm going to give you, this is historically and mathematically and conceptually one of the most important ones. So this equation, this is on your equation sheet, is F equals big G, M1, M2 over D squared. Sometimes if you're talking about like the Earth orbiting around the sun, you'll see it as big G, M1, M2 over R squared. Okay? So basically what this says, this F is the gravitational force between any two objects. And the only criteria that you have to do this calculation are 3 things. You need the masses, and you need to know how far apart they are. Okay? That's it. So what this means is that Bailey is sitting back there. If I know her mass, and I know the mass of that red fire extinguisher that's behind her, I can calculate the gravitational attraction between Bailey and that fire extinguisher. Okay? You all are gravitationally attracted to each other, to the table, to obviously the strange rock that we're on. Okay? You are gravitationally attracted to the sun, the moon, Jupiter, Saturn. You are attracted to the most distant electron in the most distant galaxy no matter where you are. So when someone says, oh, you're in zero gravity, okay, the only way, the absolute only way you can technically be in zero gravity is if you are this is the ultimate freshman mentality, that you are the only thing that exists in the universe. Okay? Like if you are the only thing in the universe, that's the only way you can be in zero gravity. Because if there's any other mass anywhere in the universe, you're going to be gravitationally attracted to that. Okay? Now, let's talk about this big G. So this big G is called the universal. Oh, I hate my pen today. Seriously. Maybe my pen took vacation. Universal. And this is, if you look on your equation sheet, this number is up there. Gravitational constant. And that has a value of 6.67 times 10 to the negative 11th newtons meters squared over kilograms squared. So what I would recommend, we're going to use this number a lot, okay? All of your calculators should have like the ability to store a variable in your calculator. There should be like an STO button or something. I would highly recommend that you store this number because that way you don't have to type it in every time, okay? And when you do this, listen to me. Punch in 6.67. Do not hit the times 10 key, okay? Hit the EE key. So go 6.67 EE. Some of them might have it as EXP for an exponent. And then to the negative 11th. If you have like an alphanumeric option, you might store that as G, okay? Because then you don't have to worry about, oh, I'm going to store that as G. There's going to be a whole bunch of constants that you're going to need. This is going to be one of the most important ones, okay? And here's how you can check that you have this right. If you hit recall, and again, that varies from calculator to calculator, but if you hit recall and multiply that times 1, you should get 6.67 times 10 to the negative 11th, okay? So that's how you can check that you stored it right. Store the number, recall that variable, multiply it by 1, see if you get that value. Now, here's the odd thing about Newton. Newton was a big picture kind of guy, okay? He was a big picture guy. So he never actually found the value of the gravitational constant. He just said, hey, the gravitational force is proportional to mass and it's inversely related to distance, okay? That's all he said. Because somebody else figured the value. And so there was an Englishman by the name of Henry Cavendish. Cavendish was the one that actually discovered the numeric value of G. So what he did is pretty clever. He took what's called a torsion wire. And this is big. This would be like, this was actually about the distance across this room. This is how big this was. And he took 2 lead weights and he put them on the ends. And he actually had a room built onto his house just for this experiment. And then what he did is that he measured how much force it took to make the wire twist. It was called a torsion wire. So he would know how much force it took to make that wire twist. Then what he did is he put other masses out there beside it. So when he put those masses there, he would measure how much the wire twisted. So if he knew how much the wire twisted, then he knew how much force there was. Oh, then he went to this equation and he goes, oh, I know how much force there was, got that number, because he knew how much force it took to twist the wire. He knew the masses of the objects that were being attracted, and he knew how far apart they were. And so he was the one that first came up with a working number for G, which was tough, because it's such a small number. Now, I'm going to tell you this right now, and I'll tell you this 2 or 3 times. If there's ever a unit that you have the potential to get answers that make absolutely no sense whatsoever, this is the unit. Because if you don't square things, you don't cube things, you punch numbers wrong into your calculator, you are going to get answers that make absolutely no sense. Because some of these answers are going to be really, 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 really small. Like, for example, we're going to calculate the attraction, gravitational attraction with Bailey and that fire extinguisher. Okay, oddly enough, that's going to be a small number because I don't have to worry about here. I'm up here lecturing, and then all of a sudden, the fire extinguisher flies off the wall and starts to accelerate towards Bailey. Okay, which would be cool, but it's not going to happen. I didn't have to leave that as a sub note. Oh, by the way, if there's a chance that the calculator might fly off the wall and accelerate towards one of my students, it's just gravity. Don't worry about it. Okay, not a sub note that I left. Okay, because I know it wasn't going to happen. You're going to get answers that are really, really small. We're also going to get numbers that are really, really big. Okay, like we're going to calculate the mass. Eventually, we're going to calculate the mass of Saturn or any of the planets. We're going to calculate the distance between us and the moon. Okay, we're going to have some really, really big answers as well. But if you don't do these right, it's going to be an absolute train wreck in terms of your answers because they will make no sense whatsoever. Okay, so let's say we want to calculate the attraction between Bailey and the fire extinguisher. Okay, so is my pen really going to die today? So we've got big G, 6.67. Times 10 to the negative 11th. Now, the units will make sense in just a second. That's newtons meters squared over kilograms. Now, let's say Bailey has a mass of 50 kilograms. And let's say that the fire extinguisher has a mass of 2 kilograms. And let's say that they are 2 meters apart. And that's going to get squared. So this is why it has the wonky units that it does. So this is why it's newtons meters squared over kilograms squared. Because when I multiply kilograms by kilograms, I get kilograms squared. Oh, that's gonna cancel that out, okay? And then I'm dividing by meters squared down here. That's gonna cancel that out. Boom, I have newtons left, okay? So, make sure that you can do this. So somebody, take my word for it. Do this calculation and let me know what you get. So basically, it's 6.67 times 10 to the negative 11 times 100 divided by 4. If you really want to get fancy, you can just multiply it. 6.67 times 25, it's the same effect. Let me know what you get. It's going to be a really small number.
I got 1.6675 e to the negative 9.
6675
Yeah,
times 10 to the negative 9th.
yeah.
Anybody else get that?
Yeah.
Huh? Yep, we're cool. Nice. Okay. All right. So that's obviously a pretty small number. Okay. So like a 1 kilogram mass weighs 9.8 newtons, right? So, but here's the cool thing that would happen. If Bailey was floating in space, okay? If Bailey was floating in space with the pen that didn't write, okay, so here's Bailey. Pretend that there's the fire extinguisher. There's the fire extinguisher. There's Bailey, okay? So if they were floating in space, that would be the attractive force between the two of them, okay? Now, it's not going to be very much, okay? It isn't like you put them in space, all of a sudden, okay, and then go like this, okay? It's a small value. But they would begin to pull on each other. Now, this is also where Newton's third law kicks in. Don't look at this and go, oh, Bailey has more mass. That's going to be more force acting on her because she has more mass, okay? This is Newton's third law. Both of those objects are going to have the exact same force acting on them. Bailey's going to feel that force. The fire extinguisher is going to feel that force. And so what you would see over a period of time is that they would slowly begin to drift towards each other. Now, here's the cool thing. As they drifted closer to each other, what would happen to the gravitational force between them? They're going to drift towards each other. What's going to happen to the value of that force? It's going to get stronger because we're getting closer, right? It's an inverse square law. So what would happen is that as they are drifting towards each other, that force is actually going to get greater and greater and greater and greater and greater. So the acceleration is actually going to get faster and faster and faster. So it becomes like a positive feedback loop. So the closer they get, the stronger the force is. The stronger the force is, the greater the acceleration is. The greater the acceleration is, the faster they're going to close in on each other, which is going to create even more force. So this is the cool thing about gravity in terms of allowing stars to form. If we didn't have gravity, we wouldn't be having this discussion, because after the Big Bang happened, if there was no gravitation, we really don't know why the universe has it, but what happened it does. And if that gravitational force wasn't there, hydrogen would never begin to collapse and get denser and denser and denser and heavier and heavier and heavier, where you form these massive collections of hydrogen. You would have never got stars that form, okay? So without gravity, we wouldn't be here. Now, the 6.67 times 10 to the negative 11, that is a universal gravitational constant. So what that means is that as best we've been able to observe, no matter where you are in the universe, if you're on Earth, Mars, Jupiter, Proxima Centaurus, doesn't make any difference. That number never changes. That's why it's called the universal gravitational constant of 6.67 times 10 to the negative 11. Now, an interesting thing's going to happen, okay? So this is the value of this force when Bailey is 2 meters away. She's going, oh, you know, it's kind of creeping me out, okay? It's like, oh, you know. So Bailey's going to get up and she's going to walk away, okay? So Bailey's gonna go, I kind of feel this, I don't like it. So she's gonna walk. And instead of being 2 meters away, Bailey's now gonna be 4 meters away. Okay, so she's gonna double her distance. Okay, so she's gonna double her distance. So she doubles her distance. We'll do the numbers in just a second. Stop that camera. I'll send you guys what you all missed.